The ACT section of, let me welcome everyone to this meeting of the ACT section of RINA, a technical meeting and our presenter tonight is Dr. Francois Flocard from the University of New South Wales in Sydney at the Water Resources Laboratory. My name is Warren Smith. I have the privilege as the chair of the ACT section, and I welcome you to this meeting. We do have people in the meeting from around the country, so that's one of the benefits that COVID has brought us, to broaden the audience for these presentations and bring us together a little more strongly, perhaps as a community within RINA. But turning attention to introducing Francois, Dr. Francois Flocard, an expert in the field of renewable ocean wave energy, and he's managed the installation of a 250 kilowatt pilot device in Victoria, and has led several large studies related to wave dynamics and wave energy conversion processes over the last 15 years. So he's certainly an expert in the field. He's also worked on projects of coastal hazards, coastal structures, climate change adaptation, physical and numerical modelling, and coastal monitoring from an oceanography and ocean engineering, coastal engineering perspective. Francois actively involved in collaborative research work, author of over 20 peer-reviewed publications related to the assessment of climate change effects in the coastal zone, as well as innovative coastal protection solutions and wave energy. I first met Francois while I was visiting WRL, the Water Resources Laboratory in Manly last year, and he kindly accepted the invitation to make a presentation. Where we started was sort of around a discussion of the Australian wave environment, and he's tailored the talk to include that, but also its impact or the opportunity that arises for renewable energy. So the title of the talk, as we've published, will speak on the Australian wave and tidal environment and the inherent marine renewable energies. So without taking further from what Francois may have prepared, I'll hand over to him. And thank you once again for speaking to us tonight. Francois.
Thank you. Yeah, so please just, don't hesitate to jump in if sound is bad or make a sound, because it's always pretty daunting, I think, nowadays in our Zoom presentation to have absolute silence. So Warren, sound is good? Yeah, okay. So, and just to maybe also give a bit more context on this presentation. So I think, as Warren mentioned, I really come more from a coastal engineering perspective. So, I understand that it's a very different audience to what I would typically interact with. But yeah, my background is in mechanical and civil engineering. I did a PhD in wave energy, which I think is the closest I ever got to naval architecture, having to deal with BM models, center of buoyancy of mass and added mass, and all of this. But then after that, got really more into I would say coastal engineering and the coastal fringe and others. But still, marine renewable energies, for me, a topic that is always fascinating. And in the last 15, 20 years, it's been very interesting to see how they have, I guess, like, you can make a lot of wave and tidal analogy of ebb and flows, but I think they're still in this process, obviously, compared to other renewables that really have witnessed the massive adoption that we've seen, progress, lowering of cost. Marine renewable are, I would say you can still say behind or on the sidelines. I think it depends on how optimistic, pessimistic, or neutral you want to be on this. But they're very different, and that's what I will spend a bit of time is talking about the very different kind of marine renewable existing and technologies. So I mean, this is the outline, but basically, yeah, starting really much on marine renewables. What are they, and what really the breadth of these renewables? Sorry. Then focus a bit on the tidal and ocean wave resource in Australia, and because it's more my field, I'll talk about wave energy conversion a bit more in detail, because I guess it's for some reason it can take a bit more time to go through all of it. And then conclusion, which really will talk about, I think, where marine renewables are and what are promising avenues in in the new, I think, concept of decarbonization of the economy and where they could come in. So marine renewables, I guess, on the left is maybe what, when people talk about offshore renewable, consider. I mean, mainly offshore wind, floating PV, but then ocean energy. And that's what I'm going to be talking on today. I won't be touching on offshore wind and floating PV. I'm really talking about ocean energy. And that is effectively conversion of effectively energy stored in ocean waters. So there's four main types, which are, I will start from the bottom right, salinity gradient, then ocean thermal energy conversion, also known as OTEC, then tidal energy, and then wave energy. So I will start the talk by going through these four main categories. So salinity gradient energy is effectively the type of renewable energy where you aim to convert the difference, basically the energy that can be harnessed from putting in contact two fluids of different salinity. So if you think about a river estuary where you got your fresh water mixing with your salt water, and if you create a system which is on the left of the figure, where basically you have two chambers, where in one flows salt water and the other fresh water, and these chambers are separated by a semi-permeable membrane, naturally the salt water will want to flow into the fresh water. So if you have this chamber closed, then you basically create a pressure buildup, which in turn can produce electricity through a turbine. On the right is a photo of, so basically this phenomena, this technology is commonly referred as PRO. It's pressure retarded osmosis. Osmosis like in desalination due to the membrane. And on the right, you see a photo of a plant in Norway that was built and run by Statkraft, which is effectively the national Norwegian electricity provider. But just to give a sense of, I guess, the size of the plant or the electricity production based on the size of the building, it was like they were achieving 10 kilowatts. So this is still very, very new and a very small niche market or technology. There are other type of salinity gradient energy conversion that are coming online, some that are more akin, if you would think about as a battery, where basically you've got a series of chambers, anode and cathode, and they work with basically the electrical basically current flowing through and difference between salt water and fresh water. But they're all very, very small. We're talking about 5 to 10 kilowatts at max, and really at the early R&D stage. What is really interesting in terms of the future potential of salinity gradient is that all studies and all technology, be it membrane-based or electrical anode cathode-based, show a real jump in efficiency of the energy conversion process when you have the difference in salinity gradient between the two fluids. So effectively where this gets interesting is that if you think about a desalination plant, which releases highly concentrated brine water, which typically gets in contact with, normal seawater where it gets diluted. And so therefore you could potentially have effectively a source of energy recovery, which could be potentially associated with a desalination plant, which, as some of you would know, are big energy consumption plants. So something that basically research is looking really at. Right now, the biggest hurdle for this is the cost and the viability, the reliability of the membranes. So I would say that it's a field that will progress greatly in the coming years due to effectively the advance that membrane technology are getting all around the world with desalination, but still very small and niche. Then the next one, so as I referred to as OTEC, Ocean Thermal Energy Conversion, is actually pretty old. The first OTEC plant was installed for a few years in the French Caribbean by Mr. Darzenval, which some of you would remember from your thermodynamics studies. But effectively, the concept is rely on a few things. Is that when you look at ocean waters, if you go at around 1 kilometer depth, you've got constant all year long ocean depths, water temperature up about 5 degrees. So now if you go to the surface and you're in the equatorial or tropical zone, you on the other hand have at the surface water about constant temperature waters of 20 to 25 degrees. And the idea is that if you look at the schematic on the bottom right, you effectively pump up the cold water, and you pump also the light blue cyan. You pump also what was through a warm water intake, the surface water, and you effectively use them as your cool and heat exchanger for a closed loop heat engine, where you could have, like, for example, ammonia as a low vaporing point fluid, which you vaporize in contact when you get in contact with the heat exchanger, getting the surface water, and then you cool it. It basically vaporizes, it activates a turbine, you produce electricity, and then you condense it again using the fresh water. So I guess in terms of renewable energy, this one obviously has a very good capacity factor. It doesn't deal with any predictability, as it's basically a constant resource. In terms of where we are right now, the two biggest operating plants are, one is in Hawaii with 105 kilowatts, and that was developed jointly with Lockheed Martin. The other one is very similar in size and visual. It's not on a photo here, but it's in Okinawa in Japan. And where it's getting interesting is that, again, talking about like synergies, is that it is working on, or it's installed or co-located with an aquaculture terrestrial farm. And where it's getting interesting is that when you pumping from the deep water, from the 1 kilometer zone, ocean water, these waters are typically very nutrient rich. So they actually pumping the cold water to make the 100 kilowatts OTEC work, but they're also using the cold water to a certain extent, or part of it, to get to provide nutritious water for the aquaculture. The slide on the right is so KRS is basically the South Korean CSIRO, and they have developed this floating barge, which has a rated capacity of 1 megawatt OTEC, and this project was sadly slowed down due to COVID, but the goal of this barge is to go to first in Kiribati in the South Pacific nations, where it's get quite interesting is that due to the nature of these islands, effectively from the shoreline, once you pass the fringing reef, you typically have 1-to-1 slopes. So it's very easy to get to 1 kilometer depth while staying close to the shore and your target infrastructure where to deliver the electricity. So that's going to be quite an exciting OTEC project that is going to come online hopefully in the coming year or years. In terms of OTEC project around the world, I'll go back through the map that you can see here, where basically the red zones are the areas of interest. There are a lot of projects, but I guess they are the only project pending, I think, final investment and in infrastructure in the Caribbean, but also in Southeast Asia. So it could really, we could witness a big jump in OTEC adoption, I think, in the next decade. Then going, I guess, from I guess the less maybe known marine renewable to a more classical, I guess one that some of you would know is tidal. But I think it's important when we're talking about tidal energy to differentiate tidal range, which is basically the harnessing of, I would say, the potential energy from the tide, so the difference of height through the tidal cycle in your water, as opposed to what I will talk about is more tidal currents. So tidal range, the map at the top show effectively a map of the range of the tides in centimeters, but obviously they are known hotspots, I would say, of very high tides scattered all around the world, and that is for a range of different reason. But typically, when we're talking about tidal range sites, you definitely want a tidal range of in excess of 1.2 to 1.5 meter. So it's Northern Europe as a great resource. Canada also is as a good resource, as some of you would know, and I will talk about, like Australia has also a great tidal resource, but in a very specific spots. In terms of the technology, it's effectively rely on something very similar to more classical hydraulic energy in dams, where you basically have a low head turbine in an infrastructure. Where it differs is that instead of getting your water level in your dam, raising and then releasing it, what you do is you let the tide get trapped behind the tidal, within the tidal basin. You close your sluice gates until the downstream, in a way, goes to low tide, and then you release it in a controlled manner every 12 hours. In terms of projects that have been using this kind of technology, the first one was in France and built just after the Second World War with a rated peak capacity of about 200 megawatts on the River La Rance. This is a more recent one that was open in Korea. And what you would see is that initially this was a big civil engineering project to basically cross a very large river estuary. And they actually integrated the 4 turbines that you can see the wake on the left of the photo within this civil engineering project with the peak capacity of 250 megawatt again. Where tidal range gets, I guess, more problematic is the fact that, as you would with a dam across a valley, is you're effectively having a big impact to the flow of water within I would say the tidal cycle, and so it has some ecological consequence, as well as siltation and change to the patterns of basically the sediment in your river system, which is very dynamic. So the next kind of, I mean, the two different tidal ranges, the other is tidal currents. So just the little image on the bottom is what tidal turbines look like. They effectively the wind turbines of the ocean, you could say. So typically you've got a gravity based on your seabed. You've got a nacelle with an horizontal 3-blade turbine. I will talk about this a bit later. And you effectively harness the tidal currents during the peak tidal flow. I guess the upper diagram is just to just touch upon something that is quite interesting in tidal, but also in wave energy, is that on the left you've got what is currently today a representation of a 2 megawatt offshore wind turbine, and with a Boeing 747 to give you the sense of scale of the blade and the span. A 2 megawatt tidal turbine, which exists, is represented below. So obviously far smaller. Why? Because we're not dealing with the same fluid. We're dealing with water. It's a significantly denser fluid. Typically, they're installed in about, so in the last 20 years, they've been installed in water depths of 20 to 40 meter. And to the sites that are identified for such projects need to have like peak velocities of 3 meters per second. So yeah, that's one of a recently retrieved turbine, which had been in operation for 3 years in Scotland. And that was post-retrieval. And this turbine is expected, or already has maybe been redeployed, because that was sort of basically, they're still like semi-R&D projects. So that was just like a check. This one specifically, I believe, doesn't rotate when you got your tidal inversion. Some prototype or some devices are made to actually the whole nacelle can rotate 180 degrees. So in terms of tidal resource in Australia, for some of you, this will not be news, but in terms of tidal range resource, obviously it's very site specific. It's Western Australia and NT to some extent, where we've got really, even coming from France, where I thought that our tides in north of France were really big. Obviously, yeah, these tides are really have an amazing potential in terms of tidal range. There've been a few projects, I understand, in the last 50 years that have been considered in Australia at the very early planning stage. But obviously, as you can see from this map, what's red is the resource. They are in basically very isolated areas where the economic of the project never really stacked up. In terms of currents, so now I'm talking about the, I guess, tidal current resources. You can see that I mentioned this number, or the magic number of 3 meters per second. So Australia, in a way, has some very specific tidal current hotspots, I could say, but compared to a location like Korea or again Northern Europe or Canada, maybe a bit below than some sites that have been previously identified. I think what's important when we're talking about tidal currents is that compared to tidal range, if I go back to this map, where basically the resource is really, it is very macro site specific. For tidal currents, it's very much driven by the bathymetry and the terrestrial objects. So mainly, if you think about a spot like Tasmania, so this is a close-up of the northeast corner of Tasmania. This basically this quite good tidal currents of like nearly 2 meters per second are due to the complexity of the underwater channels, but also the constriction due to the islands. So typically, these are where the sites are pretty promising for tidal currents, which also most of the time mean that they're quite close to the shore. In terms of how to better understand the tidal resource, CSIRO in the last few years have released conducted numbers of studies and released them on online GIS Atlas portals, and they're available for everyone to look at. So I would recommend that, if you have any interest of, where is the resource, it's a first pass, I would say. Atlas of the resource in Australia is now publicly available. So now ocean waves, I will spend a bit more time. That's fine with everyone, and yeah, because maybe it's a bit more of a complex landscape, but it's also a subject that I study a bit more. So, I mean, these are slides that I gave to first-year students at uni. May not have to, but still, I think it's always good to just spend 1 minute. Is that obviously when we talk about waves? What are waves? Waves is basically are created by wind. If we really go back to the origin, they created to a certain extent, offshore condition. The wind blow, basically you got your distance of fetch, and then once everything get reorganized to an extent, then it changed to swell and longer period wave. So I guess depending on where you are in the wave process creation, you already can be dealing with waves of 5 seconds, 7 seconds to up to 15 or 20 or more seconds. So you already got like a diversity, I guess, in the nature of the resource. And you got smaller wave and bigger waves, obviously. Then I guess if this is a slice of the water column, well, I hope I really am not like, using your time on things that are maybe very obvious to everyone here. But for a student, I think it's quite important to show them effectively the transformation of the, I guess, the orbital velocities of the waves when they travel from deep offshore and come to the shore. And effectively, we start offshore with an energy distribution in the higher part of the water column with no energy in past, your wavelengths onto sort of like demarcation, and the energy or the velocity field under your wave has, to a certain extent, linear waves, as much vertical, as much heave, as horizontal, as much surge. The closer you go to the shore, you start to get shoaling and transformation to shallow water waves, where you suddenly, you gradually get more surge in your velocity, more horizontal velocity under your wave than vertical, but you also have it gradually more through the whole water column. And I guess to a certain extent, it's because of this changing nature of the wave energy within the ocean that explain also some specificity of the wave energy conversion technology. A system that would work just specifically on a heave, trying to harness energy from heave, wouldn't be suitable for coastal water where you have predominantly surge. In terms of the resource, when we talk about wave energy, what is the resource? We express it when you're talking about wave energy, you express it in kilowatts per meter, and the per meter is meter of width of the crest of the waves. So you're basically saying across a meter width, the wave is passing, there's so much energy there in there. And when you're talking about numbers, obviously water is a very dense fluid. Waves have been basically harnessing all the energy from the wind for thousands of kilometers. As you can see from this map, with dark red and orange being the highest energy, we're talking about 40 to 60 kilowatt per meter. They're in the higher latitude, and also, which makes sense, this is where you got the most energetic trade winds. They also typically are found, if we're talking about the shoreline, on the western shoreline, as can be expected. And now if you look a bit at Australia compared to your Pacific Northwest in North America or Northern Europe, obviously Australia has a very long shoreline that is really well exposed to this well. So in terms of, now we zoom in on Australia, that was CSIRO also led in 2016 what is called what we refer to as the Wave Energy Atlas. So I believe this map, sorry, let me check maybe if I can get you I don't want to say something wrong. Is that, so this is the, again, the mean wave energy flux in kilowatt per meter. And I do believe, sorry, that this is given at the 200 meter isobath. And in terms of resource, we're talking really like on mean annual wave energy, we're talking about in excess of 80 kilowatt per meter for really from Perth effectively to Hobart. Where it gets really interesting with, I guess, the continental shelf that Australia has and the nature of the bathymetry is that all the wave transformation models show that there is, I think, less than, if I remember well, less than 10% of power loss between the 200 meter and the 100 meter isobaths. And then if you go down to your 50 or 50 meter contour, you still got 65% of your wave power. So you can really come close to the shore, and you still got really a good, I would say an amazing, a world-class wave energy resource. Another aspect of the wave energy resource that is really interesting in Australia is its relatively low variability. So this map, effectively, blue to yellow, show that there is, blue show that there's really not much monthly variability in your wave resource. Yellow is you start to get, a degree of variability, a ratio of 1. Obviously, the areas in a higher latitude in Australia have a very big variability, because you've seen about the wave climate over there. It's very cyclonic driven. So it is not swell driven like we would have in our Southern Ocean. So that's why you've got this bigger variability. And where I would say, I know that Warren is in XCT, but being sort of maybe more, I would say, familiar to New South Wales shoreline and wave climate, where it's getting interested is that, if you go back to the wave resource, obviously it made sense, I would say, for research, for some projects in the past to really have focused on either Western Australia, Tasmania, or others. That's where you look at the resource, you say, that's where the resource is. That's great. That's where we should go. You look at New South Wales and say, well, it's not as good. We sort of are, we're sheltered from the big, the roaring swells from the south. On the other hand, the variability in New South Wales is very mild. Like all year long, we will effectively, if I'm in Sydney, I would say, you got this 1.6 HS all year long, barring storms, but that's what you get. So you really got, in terms of renewable, a really good resource. The South, Western Australia and Victorian resources is incredibly good. But I think New South Wales shouldn't also be discarded, because it has really, on the other end, like really a more consistent wave climate all through the year. And that also, again, compared to a lot of locations in Northern Europe, which have a big variability between summer and winter, they're very different wave climate. Here, Australia has a more consistent wave climate. This is really to talk about basically the resource. I guess the more you refine, typically with wave models, the more you discover that actually, there's maybe even a bit more resource. And I think that was a study for really along the shoreline of New South Wales, where basically 15 kilowatt per meter would be a good average for your wave climate. And these are just showing the variability between your winter and your summer, which still is there, but going down maybe to 10 to 12 kilowatts. Just to talk also a bit more about the New South Wales wave climate, and not just to be a New South Wales wave energy advocate. Where it gets also quite interesting is now, maybe this would be more familiar for your field of engineering, is obviously when you're designing. And I guess, I design coastal structures, but even if you design offshore structure, this is an average recurrence interval plot, ARI, on your x-axis, or your 1 year, your 10 year, your 100 year, and you got your HS for a range of basically wave buoys that were analyzed at WRL all around Australia. So just color coded. The green lines on this map represent mainly New South Wales wave buoy that you can see on the map. The dark red are Western Australia, and I guess this line, for people that love looking at wave buoy data or wave buoy, is obviously Cape Sorel, which is an amazing wave buoy that has been deployed for multiple decades and is really an incredible source of information on the Southern Ocean. And I guess where it's getting interesting for designing any kind of structure that you want to put in a genetic wave climate is seeing how effectively New South Wales really has a nice drop in its extreme wave climate. So obviously, what you lose in your resource, you don't have maybe your 30 kilowatts per meter, you only got your 10 or 12 or 15. You also obviously de-risk any kind of project that you want to put there, because you're not dealing with potentially a 12 or 13 meter HS for your 100 year, so a 26 meter H max, but you are more in your 8 meters HS. So I think that this is where it's quite interesting that I would think that, should the technology permit, New South Wales do has an interesting wave climate for this kind of resource. And finally, I guess just to talk about the resource, I touched upon capacity factor as a renewable of OTEC, which was to a certain extent also salinity gradient. If you think about it, there's almost no variability in the resource. It's it's what you have. Tidal obviously is a quite unique fluctuating renewable that is completely predictable. Wave, we slightly get less predictable, but compared to solar, for example, we're still, the wave climate, as we all know, is pretty, I would say predictable on a 3 to 6 days basis. So if you're a grid operator, that's where, for a long time, this is where renewables were really, marine renewables were trying to make their case, is that they're allowing to give sort of like a grid stability potentially by injecting a power that is fluctuating really in a slower manner or in a more predictable manner. Well, you would recognize this. It's a different map. It's not the same of the Tidal one, but again, now if you go to the nationalmap.gov.au portal that is hosted by the Data 61 from Cyro, I think, if it hasn't changed name, you also have a really a great number of maps from your annual to your monthly variability at variable resolution, but still great starting points to if you want to really better understand the wave climate of a site. They also provide directional roses for all of this. They're numerical model outputs, but they've been using a really well calibrated wave model. So now, if we talk about technology, and I think I'll just start here. If you think about offshore wind turbine, you can see three wind turbines that were manufactured by the main three offshore wind turbine manufacturers. Pretty sure I could change the label under each of these. Not many people would be able to say, no, that's a Vestas. Oh no, that's a Siemens Gamesa. They pretty much all look the same because wind power is very mature in terms of technology. Tidal energy, tidal currents, again, yeah, bit different, but overall also it has converged now. We're talking about horizontal turbines, mounted on gravity based. Okay, number of blade can change, but still it's pretty much very mature. Now, wave energy, that's a snapshot of devices that had been deployed or were going to be deployed in 2015. Try to find a common point between all these devices, except that they're on the ocean. It's quite hard. 2020, still the same. And obviously, there's a few things happening here, is that it's not a mature technology. It's still in infancy, you could say. I guess it's a very old infant. It's now 40 years old, but it has challenges that I'm sure naval architect would understand for a lot. But there's absolutely no convergence. And some of it, as I explained, is that it's due to the fact that some of these devices are designed to work in very different operational conditions than others. So it doesn't make any sense that, it wouldn't make any designing sense that they look alike. They have to look different because they're not trying to harness the same energy. So if we try to, again, just maybe a little bit of what was the story of ocean wave energy. The first, a very famous French wave energy academic found actually traced back the first patent found was in France by this gentleman called Girard, which was basically what I understood is that he owned a fleet of vessels near La Rochelle, the port of La Rochelle, and was effectively being very frustrated by the time in 1799 to load the vessels. So it was there's waves next to the dock. It would be great if we could harness the energy to help us load merchandise into our vessels. And as you know from patents, you can put a patent, you don't have to do anything with it. And it seems it's a case, like basically this guy had the ID, but nothing happened. Then you go to Nantucket in the US in 1885, and Mr. Courtney basically patented and commercialized what was called the Courtney whistling buoy. And I don't know if it's clear from this I think quite nice diagram, is the left is the basically this buoy that Courtney was providing in, and on the right one, in the trough of the wave, you see a schematic cut of the inside of the buoy. And what do we have? We effectively have an open tube, and a chamber, and so the drawing is technically not really correct, but still, you've got a piston of water moving into this tube. You create an airflow, and it actuated a whistle. So effectively, that was basically a navigational aid that they put into some of the approach channel in Nantucket, so that despite the fog, mariners would basically hear these buoys whistling due to the waves. Fast forward to, I don't know, 1910. Again, in France, in the southwest, there's record in some engineering old publication of this gentleman, Beauchot-Brassic, which basically had a house on a cliff next to a blowhole. That's what basically was the story. But he was like, okay, yeah, what can I do with this blowhole? And he capped it and basically harnessed the airflow again with basically a little turbine. And while there are records that he was basically producing energy. But in terms of modern marine, ocean wave energy conversion, the main one is basically the work done by Mr. Masuda in Japan, which is quite interesting because basically it's a mix of the two previous projects that I mentioned to you guys, the whistling buoy and the blowhole. And what he did was effectively really, instead of using just the air piston to do a whistle, then there was onboard basically turbine on these buoys that could be powered, and powered the light, powered the sirens, and produce a few kilowatts of or I think a kilowatt of power. They were deployed. My understanding that there were nearly hundreds of these buoys that were installed along the shore of Japan. But slowly, with the advent of solar technology and onboard batteries, they gradually got phased out. But so now, if we talk about wave energy converters, and we try to make sense of the photos that I went through initially, sorry. So the first one, let me try to reactivate this slide. Yeah. The first category of a device that we talk about are usually referred as oscillating water column. Your waves and part of the energy of the wave enter a caisson or a chamber, basically create an oscillating movement of a water piston into the chamber, an air piston, and then activate a turbine. As I'm sure you would in your field of work know the concept of resonance. Chambers are typically designed to actually have basically operate well to resonance, to basically have a more even marked vertical motion of the water within the chamber. In terms of installation, fixed or floating. So fixed, this is an example of a plant, an oscillating water plant in Mutriku in the Basque Country in the north of Spain. So the project, again, if we're talking about synergy or co-location, is quite interesting. You can see the old harbor of Mutriku in the back of the photo, and they had to basically enhance the protection capacity of the breakwater for their fishing fleet and aquaculture. So during the design process, it was not the early stage. I think this was a bit tacked along, as you could see from the design, but it was like, okay, we're building all of this. Let's try to actually, we have a good wave resource because we know it, because we need to build a big breakwater. Let's they basically let's use this infrastructure to also try to harness wave energy. And that was also, I mean, it's also a research facility, but what you see from the concrete fan that is extending or protruding from the breakwater is there basically 10 different caissons with 10 separate openings, to which this is the next photo is inside the breakwater. You effectively have basically 10 testing spots for turbine designers and operators. But in the last, in 2019, a milestone was reached of over 2 gigawatt-hour of power produced by the breakwater. And nowadays, it's basically producing power for about 100 to 150 homes through the year. Closer to us, I mean, this was to illustrate the fixed structure, floating structure. Some of you may have heard about this Australian company called Waveswell that deployed just at the early 2021, effectively a floating oscillating water column. You see on the left the concrete chamber that was being built, I believe in Victoria, and then it was, but effectively this is mounted within a sort of, maybe I'm not going to say it well, but a twin hull system. So it was actually floated and towed across the strait to King Island, and then they can sink it and or erase it by just filling or emptying ballast tank. The rated capacity is about 200 kilowatts. What's getting interesting for King Island is that it's effectively King Island relies on diesel, wind, solar. It's just trying to basically use a remote site to trial basically a novel source of renewable in a mixed grid. Then where a lot of the diversity comes from is a lot of wave energy conversion work on what is referred to as oscillating bodies. So this body, a floating body, get moved by the passing wave, by the velocity field of the wave. It reacts against typically you would say a fixed frame of reference, and you basically extract work from this motion, typically linear or pitching motions that you're trying to harness. So this is an example, and this, I guess, this really illustrates the range of type of technology. So if I start from the top, this is basically a heaving buoy. So this would have been designed and deployed in deep water. So mainly working with heave. I understand that under the hull of the buoy, you would have like basically a reaction plate, so that you basically are effectively letting the buoy ride up and down the wave. You have a hydraulic oil system that you're basically pressurizing your fluid and converting to electricity through a motor. The Wello or Penguin, which was deployed in Scotland as a research facility, operated far more like basically on pitching. And basically, it had, I think, a system that sort of, to summarize it really coarsely, would be like an inertia wheel inside. So you basically have your pitching motion that is basically actuating this inertial wheel, and you're harnessing more like a pitching motion. Down on the left is, some of you would know, I'm sure the people from Western Australia would, it's a Carnegie Cito buoy. So this big float was basically tethered to the seabed below the surface of the waves, and was basically being pushed by the waves passing above it. And again, like the tethered was effectively pulling and against a big hydraulic jack, which was then pressurizing the fluid and producing power. This device that has been installed in Trafalgar and south of Spain. I think hopefully it's clear enough, but basically these floats goes up and down. You've got your hydraulic jack, and you're pressurizing the fluid to power a hydraulic motor. This device, which I think I've got another photo because that was a generation one. These big red, they're sort of rectangular paddles. So when this barge is lowered to the seabed, they are buoyant. So they would stand proud vertical, and the waves are just like pushing on them, and you basically are harnessing a very slow moving rotation movement. One of the last category is usually referred to as run-up. So I hope that the run-up device, so you effectively have a structure that let the wave overtop it. You create basically a head that power a low head turbine. And this was, for example, retrofitted into a breakwater in Italy. So you basically have your waves running up on the left ramp and basically contained in this chamber and released below. In terms of farms, so Tidal, so as you could expect from a more mature technology, Tidal now has the main array that I would talk about, like which you imagine is like a wind farm, had 4 to 5 turbines deployed together near Scotland with a peak capacity of 6 megawatts, and where has been producing. Some of the turbines have been removed, as you can see on this vessel, but they've produced, for periods of in excess of 6 months continuously, and I think about 10 gigawatt hour produced in these arrays. So pretty reliable kind of system. But I think it shows also, on the other end, the sort of infrastructure or equipment that is required to deal with these installation. Which these vessels are typically. I mean, if Tidal Energy also got a good head start in Scotland, it's also because of all the oil and gas industry and the availability of this equipment, but obviously very costly. Wave farms, I would say, or wave energy farm, because of the fact that this is still in R&D, a lot of them are considered wave farm, meaning that multiple devices are installed together. This is schematic of one that is currently being developed in Oregon, but effectively what you have is it's test beds for developers to be able to come with a device offshore, connected to a subsea hub or a subsea cable, so that basically electricity production can directly be brought back to shore. And the onus is only on the deployer to look after the development of its device. There's a couple of them around the world. The most famous one is the MEC in Scotland, which I think in the last 20 years had nearly 50 devices tested over there for a duration from a few weeks to 2 years. In Spain, BMEP also recently had basically a lot of its subsea infrastructure, multiple test berths installed, and can basically welcome developers to test their device. And the site that we can mention is also Gunner Island in West Australia, where CETO actually had 3 of their devices operating for, I think, a period of a few months, with a rated capacity of 700 kilowatts. Oh, sorry, I should have gone faster, but yeah, again, the SPAC wave in the Northwest, but also Albany more recently, which I will talk about after. So now in Australia, what's currently happening, I would say, and research-wise, I'm just putting a few of the universities that I know are active in there. It's not to say that others are not, but I will just touch upon, I think, the big players. So the first one would be the University of Western Australia. So the logo that is above the Marine Energy Research Australia is effectively they have a satellite campus in Albany that they are currently using as effectively a test bed for marine renewable. So the idea is that they've installed wave buoys to better understand the resource, but it would be also to integrate with the industry to try to accelerate the deployment and facilitate the deployment at sea of such devices. But the other project that UWA is working on and hopefully will deploy at their test site in Albany is called the M4. So on the right, you would see a CAD representation of the systems. So you basically got these multiple floats of different weight and diameter that are articulated around the center. And basically the idea is to create a platform that can extract energy, but still also provide basically support to infrastructure, such as for aquaculture or other systems. The other really very active, I would say, leader in marine renewable would be the University of Tasmania and AMC. They are the leading entity. They're not the sole entity, but of basically this CRC, so this Cooperative Research Center called the Blue Economy. And I don't know if some of you would know, but basically when we talk about blue economy, it's basically offshore engineering, renewable energy or energy production at sea, but also seafood and aquaculture and fishing industry. And basically they're looking at the fact that those are all high growth sectors of the industry, or flagged to, like the aquaculture and marine resource production are really flagged in the next 50 years to go through a lot of development. It's like, yeah, there's definitely need to collaborate, is that we need to develop an industry. This industry has specific energy needs. How can we better basically work in a co-location and a collaborative manner? And those are some of the projects. And there's many projects. I would recommend that you go to the Blue Economy website to learn more, because they're really also trying to do, being a research center, basically they really make an amazing work to disseminate the research that they're working with other university, but also with industry. Then my little field, I will just pitch mine. The Water Research Lab is in UNSW is really one of the birthplace of coastal engineering in Australia, and that's where I really work on. And basically, the idea is to investigate the possibility for any kind of marine renewable deployments, in this case, wave energy farm, to act or to basically be able to switch from a power generation mode to more coastal protection mode, but also to assess the potential consequences of such deployments in the future. And I'm just illustrating it with detached breakwaters on the left, sorry, which are well known to in the past to have been successful, for example, to help for beach growth and protect it from coastal erosion. The thing also that needs to be understood is the potential effect of removing energy to a very dynamic system such as the coastal environment is also twofold. Like you can basically hinder the recovery process of beaches. So that's what we're looking at through numerical modeling, but also physical modeling. We have a new wave basin now where we're going to put, we love putting sand or different kind of material to look at the evolution of beach forms. And yeah, we'll basically look at this, effectively trying to assess the spatial distribution of arrays of devices, but also when they're operating in a power extraction versus a beach protection mode. So in terms of industry, I talked about Carnegie Energy in Perth. So this was really a big project that they worked on in the 2000 and 2010s, leading to the deployment of the 3 buoys that you've seen and for a duration of 12 months. Since then, there was financial difficulties, like every wave energy company when they try to really leave the pure research world or world of university and try to deploy. It's not uncommon. They went through, I think, a difficult period, but now are really bouncing back. And I think the idea that they are part of the CRC Blue Economy is, if you look at the system that they were working on of these floats tethered to the seabed and basically tethered, pulling, and basically extracting energy this way, they are now working on a project where the picture on the bottom right with the fancy electrical blue is basically the concept is basically this is a feeder barge that is used in Tasmania to basically bring the food to the salmon farms. Effectively, these barge needs to stay in position during the feeding process for quite extensive duration. So the idea is actually to have an energy recovery system as a tether for the barge. So a bit like, I think if the closest analogy I would have is sort of like regenerative braking on trucks. Is like, you basically now use your mooring to actually recover some energy. Waveswell, so this oscillating water column project that I mentioned that was deployed in King Island, I guess, where the snapshot on the right is actually a live screen capture from, if you go to Hydro Tasmania King Island, this little widget is always running live and shows effectively live what is the consumption or the origin of the electricity produced for King Island. As you can see, there's no wave yet, but the idea is that I took this snapshot, I think, 2 hours ago, and obviously solar was not really working well at this time. It was night, but it just showed the reliance of a location like King Island still on diesel. So I think that in terms of decarbonization of the economy of our world, it's just like we're adding a bit of another resource will be welcome. Another and the last industry I think example that I would show is it's a company that called Bombora. I mean I think some people in Australia will still claim it Australian. It was developed initially in Perth, also at AMC, but then the company, for reason of funding, moved to the UK and Wales, and this is where they've relocated the whole company, and this is where they will develop and install their first project in 2022 or 2023, and it's very novel. I would say it shows again, like I was not even able to capture to a certain extent this system, or maybe the closest would be oscillating body and what I showed before. And so the idea is, if I start from the bottom of this mock-up that potentially they're also seeing in the future installed, is each of these basically pods that you see are these yellow chambers. They're fitted with a membrane on top. And what you have basically is the wave passing on that are going to push on this membrane, and a bit like an oscillating water column, they're going to create an airflux. So these chambers then are ducted, connected to a turbine, and you basically got an airflow and production of electricity. So I think the first devices, these two devices together, will be rated to nearly 1 or 2 megawatts, so big devices. But they've recently have been approached or are working now in collaboration with a Japanese offshore wind developer to try to integrate them actually in their floating frame. And so I guess that's where for me the conclusion are, and I hope that I kept everyone interested, is that I think for marine renewables to further develop, I think it's not realistic to think that in the next 20 years they're going to solve like a utility scale production of electricity. The solar and wind in terms of renewable, their levelized cost of energy now has diminished so much that it's going to be very hard for marine renewables to be able to compete. So I think it's really more, where does it make sense? Where can they bring something? And I think the two main elements I would say that this little plot shows is like power at sea. This is still something that we're really obviously producing energy or delivering energy at sea is very costly. So if you're able to generate there, all the better. You have a role. But also, I guess it's for remote, or I would say island communities. That's still also a place where, with my example of King Island, and King Island is not that far, it's a heavy reliance of diesel. So I really need to bring more to the mix. Again, for power at sea, it's, I think the development of aquaculture, but also what I would call the ocean of things. And those are just a few examples of very recent projects. So A few projects I'm going to show there are currently being funded by either the Department of Energy in the US or defense, naval defense in the US. So you could say to a certain extent big players. So this project basically, which would hopefully be upscale, the idea of this black device that you show is that it can be shipped in, I think, nearly on a pallet. And what this basically inflatable raft does is that through a hinging system, you deploy it, you tether it very close to the shore, but the white equipment that you see tether on top of this floating platform are desalination units. So what they're looking at is basically a system for desalination autonomous that can just be like deployed from a pier if you've got sufficient resource, obviously, but for disaster recovery deployment. And you know, they got funded by the government and are going through extensive deployment development. The other one, which is currently led by the equivalent of CSIRO in Australia, but like that is a national NRL in the US, is, I guess the schematic here show it's effectively powering, making basically recharging and communication hubs for what I would call the ocean of things, of communication, observation, and all this new kind of fleet and subsea fleet that we see around. So the top device on the right is basically a wave energy extracting device that goes to this bottom hub, which is packed with lithium batteries and can then be connected to effectively a docking station for UAVs. And again, that's being funded by defense in the US. And a last few example. So the first, the slides on the left are actually the same device. Again, that is a system that is being currently developed by Boeing. And effectively, you got this floating raft with solar panels that is also hinged, that is floating at the surface. You also basically towing this sort of like underwater glider with blades also that can also extract further energy from passing waters. And this, in this case, is just producing a few, I would say around like a few hundred watts or more. And it's basically, it's for ocean observation. So you effectively got a floating platform that's solar, but also marine renewable recovery to basically further the deployment. The fancy seaplane that you can see there is it's called the Mentor. It's this, and so the one is Boeing. This one is Lockheed Martin. That's a DARPA, so basically that's a defense project in the US. And yeah, they're basically also planning to use an energy recovery system from basically the marine currents. So they would have a system integrated in there to be able to obviously be able to a stealth mode where you don't have to go to the surface to repower or whatever, or extend your monitoring periods. The last one on the right, maybe some of you would recognize, that's the Microsoft logo. And Microsoft went through a series of experiments or a deployment. It was in the UK, where they, you can find the video on the internet if you want to see it, but basically this is a big pressure vessel. So, you know, think your big LNG tank, like not saying trailer size, but almost. But they basically have a server farm in there. And the concept with that is that server farms are obviously needed close to the demand. So if we think about in Sydney, there's a few of these like big data hubs. They're massive energy consumption users due to the fact that they need to cool from air conditioning, all their infrastructure, but also space-wise, it comes at a premium. So what Microsoft looked at is basically deploying these for a year and looking at, in terms of, with redundancy of the server farm, it's just going like, okay, do we still need, like, what's sort of like the lifespan of a servers now, when basically all the cooling is just due to the surrounding waters through the hull of the system. And they found that it was really, really efficient. So not saying this is marine renewable, but this is where it could start to look. I mean, we're talking about potentially big companies trying to install infrastructure in the coastal water on the ocean. And again, like, you know, we thought about aquaculture, but there could be a data need for a need to power at sea. And yeah, a few more examples of also project that really try to also maximize the use of infrastructure. So actually bring, you know, the energy conversion mechanism or system on existing infrastructure. So smaller needs.